since we're a bit low on time, I won't go too much about myself, but I'm in the final year of my engineering doctorate at the University of Edinburgh. I also work for a company called Sustainable Marine Energy, who design these turbines here. More on them later. So this is quite an incremental presentation in that there's a lot of steps to it, and none of them really make sense without the others. So I'm going to try and rush through each one, but if anything's not clear, just let me know at the end. We'll have a chat about it, and I'll explain everything. So starting at the absolute basics, like what is tidal energy technology? There are two different types that generally go ahead, and that's the tidal barrage, which is like a refillable electric dam, or there's the tidal stream, which is essentially an underwater wind turbine in a fluid that's 1,000 times denser than air. This is what I'm going to talk to you about today. There's been convergence on design on 2 or 3 bladed submerged floating tidal turbines. Where am I pointing this? There we go. So what are the challenges that are facing tidal energy? So our A plus B. So there's one side is the technology. There's the component fatigue. There's the maximizing the power takeoff, getting the efficiency. There's also policy, so funding options. A big one in the UK at the moment is, of course, that Brexit has ground everything else to a halt, ill-advised, to say the least. And then what I'm going to talk about today mainly is processes. So these are the O&M costs and efficiency, so learning to repair the turbines better and more efficiently. There's the utility scale or a niche, so as in, are we going to go for a grid scale deployment or maybe a microgrid? And then finally, again, the subject of this presentation is the site selection methodology, and this is something that's often forgot. So the current methodology prioritizes high resource sites to offset these other costs, and having limited access to funding and subsidies. But this kind of means that if a high-level site is prioritized, it means that you maybe end up deploying in a site where you don't quite understand all the costs and all the conditions that go there. So this is just a little bit about the company that I work for, Sustainable Marine Energy, and our platform PlayTie, which stands for Platform Inshore. It's a bit different to a lot of other turbines out there in that it's surface floating, quaternary, moored system, and it's designed to be in more sheltered, easy, low-hanging fruit conditions. So it's not going to be the turbine that you put in the highest energy location. It's the turbine designed to be easily accessible, easy O&M. So we'll just go through there. And then I've sort of just gone through this as well in that we're kind of meeting A and B. And that's a nice photo from my kayak of the turbine when it was deployed in Scotland. So the main research questions. How do metocean conditions at a site, so the unforeseen aspects of a site, contribute to O&M costs? How can we understand or estimate these O&M costs before we've actually been there? And finally, if you were to choose a site, if you do a detailed site assessment, it can be time-consuming and it's expensive, and it can also be inconclusive. So are there any alternatives? And so, of course, yes, there are. So I believe numerical modeling can help us here. So all of the models and data used in this project are freely available, and I made a point to do that because I wanted to show what can be achieved by should we say, a moderately funded tidal energy developer. Like we don't have a huge financial backing. The results of this work are not designed to be a perfect representation of what are very complex natural phenomena, but are designed to be accurate enough to inform decisions of project managers and marine renewable energy companies. So we should recognize this coastline. I decided to model the Bay of Fundy area, and so what tools have been used? So essentially I used the GEBCO data, which is global bathymetry, the tidal model for tidal constituents, and the DHI Metocean data portal for wind speed and direction data. I also used Navionics to sort of look around and find some moderately sized ports in the area. So that's a sort of plot of the depth and the ports there. So I coupled 2 aspects of the Delft 3D software suite, so that's flow and wave. Flow was astronomically forced by the aforementioned constituents, and wave was forced by the wind data and designating a reasonable open boundary along the bottom. So the results of which are that. So we've got the significant wave height there, and as you can see, the wind generally prevails to the northeast, and we get larger waves towards the the further end of the channel where you've got more fetch. So this is just one snapshot of 1 year that was modeled. And then the same for the velocity, as you would expect. Areas around the headlands, up at force here, we're getting some very high flows up to 5 meters a second. There we go. But before we can actually use that data, it's worth noting that the aforementioned plot was depth averaged. So what we need to do is actually change that into a velocity profile using a seventh law, and then we can work out our surface data and also our profile for calculating our power out. And what I mean by that, and this amazing PowerPoint construction, is that, of course, the swept area across the turbine is going to be exhibiting different flow speeds. So to calculate your power, you need to do a power-weighted average, so that equation at the top, and you put that into the power characteristics of the curve to get your instantaneous power out at any one time, at any one flow. And that's what this looks like. So this is the idealized energy delivered, accounting for these electrical losses within the system. And so the equation is used to calculate it. As you would expect, the highest energy delivered is in the areas of highest flow. Great. Except for that's not the whole story. We also need to work out how metocean conditions impact upon this. So to work out a reasonable path to shore for working out your O&M route, I initially started with a Dijkstra's algorithm over here on the left, but found it to be too computationally heavy before switching to an A-star algorithm, which essentially has a heuristic weighting, which means that it always tries to tend towards its final destination. And it also, you can set it to have conditions. So I used keeping it shallow as well. So rather than having to evaluate every point, as you can see, this one on the right is much faster. All right. There we go, and that's a very unclear example of the algorithm. So it sort of takes a nice shallow path between a port and any location within the domain. You also need some operational constraints. So the main ones to take notice of are the surface flow velocity for transit and operation, 2 and 1 meters a second, and the significant wave height, 1.5 and 1 meter HS. Using the A-star algorithm path, you can then work out your transit time to site. And so as you can see, the further you go and the further you go from the shallows, the longer your path is. So then you can use your tidal flow data and your operational constraints and your A-star algorithm path to work out your viable slack hour duration within a month. Oh, wait for time. Yeah. And so as you can see, for both transit and for time on site, the least amount of available time that you have is in the middle of the tidal race, which of course makes sense. Anyone that's been out in a strong tidal area will know that the likelihood that your tidal flow will stay below 1 meter a second for more than a few hours is very unlikely. So within, say, a month, you maybe have 50, 100, maybe less hours. And so that's the time where you can do your operations. Waves, however, are not so easily done because tides are very predictable. So we know when those 50 hours will be. Waves, however, you need a more probabilistic method. And so I use the Weibull distribution to essentially model a wave spectrum. And then this is what the access hours and waiting hours look like. So from the Weibull distribution, you can calculate essentially it's used for fatigue calculations, where it's not just the amount of access hours you have, but the likely waiting time for said access hours, if that makes sense. And so notice the scale on the right here. Essentially, the areas where you have high tidal flows and high waves are areas where you are most constrained and where you're going to have the longest waiting time. Yeah, and then that's sort of showing more of the same, but accounting for waves as well. Ignore this bit along the bottom here. That's essentially a boundary artifact. So if you remember the previous plot where we saw our high energy delivered, this actually means that it has an impact on the energy delivered because we can't produce at certain times due to downtime. And so you can see a big chunk is taken out of this top right area in force. Some other areas have lost generation simply because we can't get to the site in time and we can't repair it. If we're waiting for 100 hours a month to make a repair, we're not generating during that time, and that's a loss of revenue. In order to calculate the cost of waiting for these operations as well, I use a standby contract. So I won't go into all the different types, but essentially keeping a vessel on standby and having to pay a certain cost per day until the operation goes ahead. And then that's what this looks like, in that these are the operational costs. So the highest operational costs are seen in areas far from a port and where the highest flows are. So everything I've just said has been trying to develop a more holistic view. This plot here shows what I would call the usual site assessment method, in that all it takes into account is flow speed, generation, electrical losses, and it assumes that every operation that you perform is successful. As you can see, we're getting down to below $200 per megawatt hour, maybe even as low as 100, so we're competing with offshore wind. Brilliant. Except it's not true, because when you take into account all of the O&M costs, your plot ends up looking more like this, where there's a huge area of force that you now can't use because it's not financially viable. You're lucky to get below $500 per megawatt hour, and while this isn't necessarily pleasing, I would argue it's far more realistic for where the technology is at. So we at SME, we looked at these areas and we said, okay, well, so we know that there's high flow speeds at force, but we also know it's So here's a picture of a few of the installations here. So that's an area again away from the ground passage. And it's been in there since around January this year. It's been generating relatively well, like intermittently, and in consistent grid. And I think we're all very glad that we chose this location because we actually, even though my analysis had called for one operation a month, which was seen quite, should we say, quite generous, we actually probably ended up doing far more than that. So we probably have higher costs than we created that model. So, in summary then, spatial and temporal models of meta-ocean data have been successfully implemented. All the models and data used are freely available, so easily recreatable, easily usable. Spatial variability in the project in LCE due to meta-ocean conditions was identified. And this work, it really streamlines the site selection process by identifying areas to focus on with a more holistic view. Based on this work, we had a successful deployment and energy generation location was predicted by the model. And in terms of future work, it would be really great to increase the model duration from the only a year of models right now. We'd like to do higher resolution. These first wells were about 400 meters. And we'd like to do more complexity to better capture turbulence and things like that. So generally this is accuracy. But however, as a first pass, I think it was really useful for us. So thank you all very much.
Okay, now open for question. We have some time.
I don't want to hold the question later. I'll go ahead. So, again, this isn't meant to be an adversarial question at all. So knowing what you do about the site selection process now, and having built up seemingly like a really fantastic body of expertise on it, do you think you'd be able to estimate the UK's total tidal energy resource? And how would that compare to the total energy needed?
That is a very good question. I would genuinely love to be given the opportunity to do that. However, everything that I've done here has been from my little 16 gigawatt ramp laptop. So it's all very, very low tech. I think to model the entire UK at a sufficient resolution to actually give a good estimate with
require some access to some form of supercomputer. So if you can give me that, I'd be more than happy to take you out. But I'd really like to. I think it would show some really interesting results, because especially like the Bay of Fundy is actually quite sheltered for the most part. So I'd be really interested to see in the UK where you have to travel considerably further to get to your target locations and they're considerably more exposed. I think it would have a big impact upon like what the actual results would be.
Thank you very much.
Maybe one more question? Not,